All right, so we're going to try this with lines. We want to be able to write a line for these vectors. We want to write sort of in an equation. And so if we were writing an equation for these points on a regular line, you'd use y equals mx plus b or c, right? And if you swapped it up a little bit, you just rearrange it, you get b equals mx, b plus mx. And if you color-coded it like a true nerd, it might look like this. I want to get to this spot. I got to start in this spot, and I need to move in a certain manner, right? You got to go over and up, over and up, over and up in a certain way this many times, right? So I got to start in this spot. To get to this spot, right, I need to start at this spot, and I need to move in a certain method, right, over and up, and I need to do that a certain number of times. We're going to do the same thing with the equation for vectors, right? So this is a generic equation for vectors, and it looks scary, but it's the same thing. To get this vector, I start with this vector, and I move in this vectored format this many times. It's the same thing. So let me give you a for instance, and then we'll try an example, right? If you're trying to find, like, this can be described with this by saying, I need to get to this point, right? The way to get to that point is with vector A, right? And then to go along the line, right? Because this is trying to describe R. Probably do it in a different color. This is trying to describe line R, right? And that's line R. So it means get to the point and then move in a specific method, B, in a manner, right? So vector B shows you how to move once you're to that point, and move along that route t times, and t is your variable. Let's try an example of that, right? So they say I want to have the equation. We'll have the equation for a line that goes through this point and has this directional vector. Fine. You could think about it like this. 1, 5 is 1, 1, 2, 3, 4, 5 is right there. That's point A. The way that you get to that point is through this vector. Maybe I'll call it little a, right? And that vector is that A is 1, 5, right? And then from there, now we're trying to move. What color did I use? Red. Now we're trying to move in this fashion. So we go over 3 and up 2, right? And that's the vector we move in to follow this line. And how many times? I don't know. It doesn't matter, really. But we need to move t times in that direction, and that's the line that we produce, right? So you start with A, and then you move a certain amount of times in this fashion, right? In this slope, right? So yeah, okay. You could talk about this as t times 3, 2. Cool. And that's your line equation, right? Maybe it's R, right? So you'd say, all right, R should be that. Cool. Guess that's not necessarily a vector. Cool, so there's our solution. Should be the same. Yeah, right. First you got to go to point A, and you do that by vector A, and then you move in the direction of vector B a certain amount of times. How many times? Depends. Just like there's a variable in a linear equation. All right, we're going to try that same thing with the parametric equations. And parametric equations sort of breaks two ideas apart, and the easiest way to think about that maybe is projectile motion from physics. If you're a physics nerd, you have come to the realization that forward velocity and vertical velocity and projectile motion are independent. They're independent pieces. So we can break the two pieces into how x velocity changes, or I guess this is x position changes. It's only based on acceleration due to gravity, and how the y position changes, and that's based on the acceleration, the velocity of the projectile. All I'm trying to say is that you can break things up into two pieces and have two equations that are describing the same thing. So stick with me on this. Oh my god. Here's our vector equations, right? We were looking at our previous equation that looked like this, and we said, hey, look, I know that. Well, let's take this piece, right? I know that vector r is really my initial vector plus my changing vector times time, and this is the same thing here, right? Nope. This is just our new vector is our initial vector plus t times each one of these. So that's this piece right there, right? We can break these up into, this is a vector equation, we can break them up into two parametric equations, which is just this piece and this piece, right? The x and the y directions. So let's try to run through an example of that, of two things working independently. So we want to find it's the same thing, right? Find a line that passes through this point with this vector and describe it using parametric equations. Well, we already found, right? We already found the vector equation, which looked like this. We did that on our last example. So the parametric equations for it are just this top part, right? X is 1 plus 3t, that's this, and the bottom portion, which is y is 5 plus 2t. That's that. Cool. So that's they're equivalent ways to talk about an equation, and we can just do things with the two of them that are a little bit different, and that's where we're going next. We're going to use like a Cartesian equation. It's a little bit tricky, but you'll be able to do it. So we know how y changes with t and how x changes with t from these equations, right? But sometimes I want to know how y and x are related. We want to put these together and solve for t, right? So think about this. In this top equation, if we rearrange and solve for t, we move the a and we divide by b1, and you're left with this, right? Do the same thing for the second parametric equation. Great. So in here, time is related to this mess, and time is related to that mess, and so time should be the same thing. So we can just set them equal to each other, right? This is this, and this is that. Cool. And then what's kind of nice about this is now you can sort of put them both together. You multiply both sides by the opposite b, and you're left with something without fractions, which is kind of cool. And then we can use this piece to solve for some things. So let's check out a little example of that. We want to take the same thing and describe with a Cartesian equation. Well, we take our parametric equations, which we just built from the last example, right? We took these two. So we started with this and this from the last example. We solve for t for both of them, and we set them equal to each other, right? So we're doing this with both of them and setting them equal to each other. And so we get this mess. And then we multiply each side by the other's denominator, right? Like that. And then we clean it up, right? This is we're just left with standard form equation of a line, which is nice because that's easy to plot, right? You can find the x-intercept and y-intercept by covering up the y and the x, and you can solve it that way. Just a little fussy note. I know that we're used to seeing gradient or slope of two-dimensional lines, and that makes sense when it's laying on the page and it has some slope. Doesn't really make sense in 3 dimensions, so when we talk, instead of saying slope in 3 dimensions, we call it the direction vector, right? How it moves when we're talking about 3D. It's just a little fussy bit. All right. The other part of this is that lines can be described in a lot of different ways. So they're non-unique, right? Unique. Just because you're unique doesn't mean you're useful. So we can describe this same line, right? This same line in 2 different ways. I know the direction vector is 2, -1. So we can either say start at 5, 4 and move in this direction vector, right? T times. Or you can say start at 7, 3 and move opposite the direction vector, t times s times whatever. So multiple ways to say the same equation. So if you're having a hard time with your answers in the back, check that you're not using a unique vector. Cool. So we're going to do two problems together and just make sure you know what you're doing. So let's try it out. So we want to find a vector equation and turn it into parametric equations for a line going through this three-dimensional point and going through in this direction. Fine. So the vector equation is sort of written like that. Let's make this a little smaller. So I know that our vector is x, y, and z, and we start at this point with this vector to get to that first point, and then we move t times in this format, right? 4 in the x, 5 in the y, -6 in the z. And from that, we can break this into 3 parametric equations, which is this piece, and the corresponding in the y and the z, right? That's this piece and the z. Red, huh? Red for z. There we go. Cool. So there's our parametric equations. So that's not necessarily difficult. It's just what to do with them after that. And okay, so we want to. This is a little bit trickier, but the same idea, right? Find the parametric equations of the line through here. Well, okay, fine. So we can either find the line from A to B or from B to A. Let's just do it for argument's sake from A to B. I think it'll be easier. So one point is 2, -1, and 4, and the other is -1 and 0 and 2. And so our equation is going to look like, how do you get to the first one, right? How do you get to A? What's that vector? And then how do you change from there to there, right? That's our directional vector, D. Cool. A is pretty easy. It's just if you want to get to point 2, -1, 4, you have to move to -1 and 4, right? And then D is the difference between these, yeah? So going from 2 to -1, we have to go down 3, -1 to 0, we have to go up 1, and 4 to 2, we have to go down 2, right? So we're going to take this piece and this piece and say, okay, first move to -1, 4, and then move t times -3, 1, and 2. Cool. So, yeah, there you go. So this is just our directional vector from A to B, and okay, oh, so they asked us for parametric equations right here. So this is a vector equation. So then here's the 2 and -3t, that's this piece. And here's -1 plus t, that's this parametric equation. And the last one is here, right, just like that. Cool. If you did it the other way, then your direction vector would be a little different. Fine. Cool. That's it. Good luck. I'll see you in class. Bye.